Hey guys, it's me. Sorry I'm not there today, but today's really just about learning a few new derivative formulas, and so it's a pretty easy one just to follow along with the video. In Teams, there are two assignments. One of them is a quote-unquote assignment that just links to this video, and then the other is the homework that goes with it. If you would, especially the people who are at home, but ideally everybody, for the assignment in Teams that links to this video, not the real homework assignment, just the one with today's date on it, if you would just click turn in, you don't have to do anything with that assignment, just click turn in on it, especially people at home, like I said, because somehow that's how the county is doing attendance, or I don't know. But anyway, just click turn in Teams on the assignment that has today's date on it and just links to this video. Nothing to do on that assignment except click turn in. So like I said, we're just going to look at a few new derivative rules, which we will add to the purple sheet. And so for the rules today, unfortunately, the proofs of these are far more complicated than we need to worry about. But the formulas themselves are actually like remarkably, awesomely simple. So if I want to take the derivative of the function e to the x, and sometimes I've been doing these brackets, I don't really have to, but remember I'm saying take the derivative of e to the x. The crazy super awesome thing about e, that special number, is that the derivative of e to the x is still e to the x. And remember, e is a number, just like pi is a number. It's just a special number that gets its own symbol. And e is like 2.718 something something. And so what I have down on that graph is a graph of y equals e to the x. And what this derivative statement tells us is that, for example, at the point 0, comma 1, because e to the 0 is 1. At that point, the y value is 1, and the slope of the tangent line is also 1. This green point has an x-coordinate of 2, so its y-coordinate is e squared. And what the rule I've circled tells us is that the y value is e squared, and the slope of the tangent line is also e squared. This is the only function that has that property. And e, kind of this seemingly like random number, has tons of cool properties. This is one of them. And so we've dealt with the chain rule before. You can see the chain rule. Haha, still funny as ever, Miss Kennedy. And so we'll do this the long way, but just once. I've been talking about getting better and better at doing the chain rule in your head. For our rules today, we're going to do the chain rule once the long way, and then instantly you'll be able to do it in your head because we'll write it down. So the long way would be to say, okay, this is y equals e to some stuff, right? So donut hole, donut. That stuff is x squared plus 4x. And so if we think of the rule that we just saw, then e to the x has a derivative of e to the x. E to the u has a derivative of e to the u, just with that fixer piece, for the same reason as we've always done it. And in this case, that exponent u is x squared plus 4x, so the derivative is 2x plus 4. And then as we've done with all of our chain rule problems, we just take this statement. So it says it's e to some crazy exponent times a fixer piece. And that crazy exponent is x squared plus 4x. And our fixer piece is 2x plus 4. And remember, use parentheses to group that together. And there it is. But what we just did by writing out the rows and columns and that kind of written organization for the chain rule is we actually have already written the more general form of this. If I have, on the previous slide, if I have e to the x, then the derivative is just e to the x. On the other hand, if I have e to the whatever, then the chain rule tells me, this is not a new thing, the chain rule tells me that that derivative has e to the u times a fixer piece, u prime. If I go back a couple of slides here, if I wanted to just consider this as the same rule, e to the x has a derivative of e to the x. If you wanted to put a fixer piece, that's my cat in the background, say hi, George. The derivative of the exponent, I'm not sure if you can hear that, but he's being very loud. The derivative of the exponent, derivative of x, is 1. So that's why this rule we didn't bother with the fixer piece, because it wasn't necessary. But our more general rule, the one that's going to be more helpful to remember, the only difference is that it reminds us to include the fixer piece. Again, that's not like a brand new thing. It's just the chain rule. And so once we have that version that has the chain rule already in it, then we can take these derivatives super fast, like the Roadrunner. And so instead of writing out y equals e to the y prime equals u, instead of doing all of that writing, what we're able to do for an exponential function, so I have a base of e, that very specific and special number, and an exponent of sine x. What we have is that our derivative is going to have the original function in it, which is crazy to me, like that's very cool. So the function shows up as part of its own derivative, and then the fixer piece is simply the derivative of the exponent. And we're finished. Using the rule, this is e to the u, that's the original function, times u prime. So we look at our exponent, tack on its derivative, and we're finished. Below that, maybe some parentheses would help make it more clear. The exponent is a slightly smaller font, maybe hard to tell. So I'm just saying all of that is up in the exponent, and I want to take a derivative. And so for an exponential function, in this case, a special base of e, we'll talk about what to do if the base isn't e. It shows up in its own derivative, which is cool. And then the fixer piece, I simply look at the exponent and put its derivative here. So if you need to do some scratch work off to the side, remind yourself that that's square root of x is x to the 1/2 rather. So then x becomes a 1, x to the 1/2, power rule brings the 1/2 to the front, and we reduce it by 1. So the derivative of that highlighted exponent is 1 plus 1/2 x to the negative 1/2, finished. Literally all we're doing for exponentials with the base of e is we're saying, okay, it's part of its own derivative, and then the fixer piece is the derivative of the exponent. The original function is part of its own derivative, and then the fixer piece is the derivative of the exponent. Done. That trick, that super specific trick that we just saw, e to the u, only applies, again, with this super special base of e, which is this number that has all kinds of cool properties. This is one of them. If my base is something else, this is a joke that no one gets anymore, but I don't care. It's still funny to me. If our base is a different number, so for example, if I want the derivative of 5 to the x, or pi to the x, or pi to the x squared, anything like that, So here, to make this an exponential function, I need the base to be constant, and then that exponent can be whatever it wants to be. So we're still going to follow kind of the same trick as we did for e to the u. I'm going to leave a little bit of space here because there's a adjustment we need to make. But it is still true that for the exponential function, say 5 to the x, it's going to show up as part of its own derivative, which I've always thought is super cool. We're still going to have a fixer piece, which is the derivative of the exponent. Okay, so again, going back a couple slides, so far this is the same. It's just with a generic base of a rather than the specific number e. The adjustment we need to make if our base isn't e, just some other constant like a 5 or whatever, the only adjustment we need to make is that we multiply by a constant natural log of a. Since a is a constant, its natural log is constant. And we'll look at examples of this in a minute. But here, those two pieces are pretty much the same as what we saw before. It's the original function and then a fixer piece. And then we just make this other little adjustment to say if the base isn't e, if it's not that super special cool number, then that's fine. We just throw a constant in front. So an example of that, which also gets at the difference between an exponential function versus a power function. We'll take the derivative of this. So what I have here, and I've done this on purpose, there are lots of x's and 2's, but that's to talk about a power function versus an exponential. So take a moment and think about which of these you knew how to differentiate before today, and then which part you just learned how to differentiate a few minutes ago. The x squared, that's a power function. The reason that's a power function is because our exponent is constant. This is more like a polynomial. This is just a boring old power function. We should know the derivative of x squared from the previous unit. The other factor here, the 2 to the x, well, that's an exponential function, because in this case, it's the 2, it's the base that's constant. And so that's the type that we just saw how to differentiate. The other thing we see happening here, hopefully it's pretty obvious, is that this is a product of those two functions, so we're going to need the product rule. And so this will help us practice the old skill of product rule and power rule, along with the new skill of exponential functions and differentiating those. So for the product rule, we'll follow the same pattern as usual. We're going to differentiate the first. So x squared, we've known for a long time, becomes 2x to the first. I've differentiated the blue, and I'm going to leave the green alone. So that's the first half of the product rule. Plus the opposite. This time I'm going to leave the blue alone, and now this is the new part. I need to take the derivative of 2 to the x. That's an exponential function, and so that's one that we just saw how to do. So I'll scroll back to that. Since our base isn't e, and actually this trick still works even if the base is e, we need this constant in front, and then the original function, and then potentially a fixer piece. So for 2 to the x, my base is 2. So I'm going to think of that as a equals 2. And so my constant multiple in front is going to be natural log of 2, because the base was 2. And the original function, 2 to the x, shows up as part of its own derivative, which is cool. And then a fixer piece. So the exponent is an x. That has a derivative of 1. So this is a case where the fixer piece wasn't necessary, but it certainly doesn't hurt anything. And again, the only real new thing today was that derivative. And for the gajillionth time, here's what we just did. I had 2 to the x. My base was a constant of 2, so I did natural log of 2. 2 to the x is an exponential function. It shows up as part of its own derivative. My exponent was x, and so a fixer piece, the derivative of x is 1. So cleaning that up a little bit, I have 2 times x times 2 raised to the x plus kind of as many parentheses as you want here, and I won't bother rewriting that 1. And there again, that answer's fine. There's a little bit of factoring you could do if you wanted, but there's no need to do that. So, finding the derivative of exponential functions comes down to this. Everything else that we've done, so being able to find tangent lines, all of those sorts of things, that still applies as well. It's just we're adding one more function whose derivative we know. Okay, moving on, kind of closely related to exponential functions, logarithmic functions, logs, if you will. And so first, just a super quick recap of what logarithms are. So in bold, I have kind of the official definition and then an example to remind us of what it means. So log base A of B equals C. What that's telling me, so log base A, that means if my base is A, it's going to take an exponent of C in order to get a result of B. Log base A says I have a base of A, so now I have an exponential equation instead of logarithmic. I have a base of A, and a log is saying in order to get this result, in order to get B out of it, a logarithm tells me the exponent we need. Okay? So that's a lot of letters. This example may jog your memory a little bit more. So log base 2 of 8. What this is asking me is if I have a base of 2, then I want to know what exponent do I need in order to get a result of 8. Okay, if the base is 2 and I want to get an 8, what exponent do I need? Well, that exponent is a 3. So log base 2 of 8 equals 3, precisely because 2 to the third power equals 8. Okay. And then below that, as we saw with exponential functions, a base of e is a little bit nicer and prettier and cooler. With logarithms, the same is true. We'll be able to find derivatives of all logarithmic functions by the end of today, but the easiest and simplest and prettiest ones are natural logarithms. A natural logarithm means the same as what we have above, just specifically with a base of e. And so this is saying if I specifically have the number e, 2.718 blah blah blah, if I have a base of e, what exponent is it going to take for me to get a result of b? So an log and an ln mean essentially the same thing. It's just that natural log, the ln, is a specific type of logarithm. And so then as an example for that, natural log automatically tells me that my base is e. That's what we have here. And then this is saying, okay, what exponent do I need in order to get a result of 1? That exponent is 0. So natural log of 1 is 0, which hopefully is familiar because when we reviewed the graph of natural log, one of the important points that we looked at was that on the natural log graph, we go through 1, 0, precisely because natural log of 1 is 0. So that's your algebraic recap. And then the derivative, this is like my favorite meme of the whole year, so I'm very sad I can't be there with you to joyfully hear all of the laughter that I'm sure is happening right now, and definitely not awkward silence. Yes. Anyways, the derivative of natural log of x. We'll look at chain rule stuff to say maybe it's natural log of something fancier, but right now just the basic natural log of boring old x is 1 over x. Notice over here that the derivative has no natural log in it anymore, right? For an exponential function, I'm going to scroll all the way back up, the derivative of an exponential function was still an exponential function. The derivative of a logarithmic function is something brand new, which is another thing that I've always thought was kind of cool, but we've established that I'm a dork, so what are you going to do? So our graph, y equals natural log of x, you can see that 1, 0 that we talked about a moment ago. I also have chosen, just to demonstrate something, the point 3, whatever natural log of 3 is. It's a little bit more than 1, but who really cares? So what this statement tells me is that at x equals 1, my slope is going to be 1 over 1. So at 1, 0, that slope is exactly 1. At x equals 3, my y-coordinate is this weird number, but my slope is actually a very normal and nice and pretty number. At x equals 3, the slope of this graph is exactly 1/3, which is weird because, maybe just to me, but it seems weird, that for a crazy graph that involves this crazy number e, and the graph looks all kinds of weird and it has vertical asymptotes, the slope of this green tangent line is just 1/3. I don't know. I think it's cool. And then as we did with the exponential, I have a log with a chain. I know. It's the best jokes today. So again, I'm sure you're all laughing uproariously while I'm not there. So just as we did with exponentials, we're going to do the chain rule process the kind of sort of long way, once, and then never again. Here, we see that we're taking, let me go with my standard colors, blue and red. So I see that I'm taking natural log of some stuff, and that stuff is x to the 5th plus tangent x. And so, if everything were normal, right, if this were natural log of x, then the derivative would just be 1 over x. So I'm going to go with 1 over u, but as always, and for precisely the same reason, I need a fixer piece of u prime. And then we go find the u prime. X to the 5th becomes 5x to the 4th. And then these trig derivatives, we should know those by now. If you don't, then keep studying. The derivative of tangent x is secant squared x. So my final answer here, I have 1 over u, which is this, times u prime, my fixer piece, which is this, 5x to the fourth plus secant squared x, again, parentheses to group that together, and we're done. There's another common way to write this, which we'll talk about in just a second, but notice again, the derivative has no logarithm in it at all. The original function did, but what ended up happening is that the stuff inside moved to the denominator, and then the derivative of the stuff inside moved off to the end as a fixer piece. And so because that pattern happens every single time with logarithmic functions, we'll just go ahead and remember it that way. So here, I want the derivative, natural log of whatever I want. It doesn't have to be just natural log of x. It could be natural log of something nastier. So as we just saw, so what I've highlighted up here, that's really the official thing. The u moves into the denominator, and then a fixer piece shows up at the end. No natural logs are there at all. It's just the stuff inside the log moves to the denominator, and then we multiply by its fixer piece. Another common way to write this, probably a more common way to write this, is just to multiply that together, say that it's u prime over u. But once again, all that's happening is that the stuff inside the logarithm moves to the denominator, and then its derivative shows up on top, or shows up off on its own as a fixer piece. And so this more general rule is helpful for dealing with other types of natural logs, and lets us do some other stuff super duper fast. So for the first one, as soon as I see a natural log and I want to take a derivative, as soon as I see that, I'm going to remind myself that the derivative is going to have a denominator in it. It's not going to have a log in it. The guy outside, just move some stuff around. So all I'm going to do within my answer is where I have sine of x, that's going to move into the denominator. That's the u in my formula. And then the derivative of sine of x, which is cosine x, shows up in the numerator as the fixer piece. That's it. This is literally your u prime over u in the formula. This question asked me to answer in simplest form, just to kind of show, again, something that to me seems awfully surprising, is that this seems like a really weird and kind of randomly put together function, but its derivative is actually something we're quite familiar with, just a cotangent function. And then the second example, there are a couple different ways to think about it. We'll talk about both of those, but if I'm just going straight formula, right? If I'm not thinking too hard, I'm just plugging into formulas, that's okay. I see the natural log, so I'm going to go for a fraction or a rational expression. The inside stuff moves into the denominator, and then its derivative shows up on top. That's the fixer piece. The derivative of 2 is 0. So this derivative is 0 divided by 2, which is still 0. We did that using just the formula, which is fine. It didn't take that long. Or if you think about it for a moment, I don't know exactly what number natural log of 2 is, right? I don't know, like I know it's a little bit less than 1, but that's kind of all I've got. What I do know is that my cat is knocking things over, and I know that natural log of 2 is a number. It's a constant. There are no x's in there. So any constant, no matter how crazy, is automatically going to have a derivative of 0. So you could say the rule tells me the derivative is 0, or you could simply say, oh, natural log of 2 is just a number, so its derivative is 0. And once again, just as we did with exponentials, this time we were dealing with natural logs. So we were specifically going with a base of e, which is a little bit nicer, a little bit prettier for calculus. But then moving forward, what if the base is something different? So then I no longer use the ln, because that specifically means a base of e. Instead, I'm going to go with an a. Once again, that a just represents some constant. So maybe it's log base 2 of x. Maybe it's log base pi of x squared. All kinds of stuff. But as we did with exponentials, I'm going to start here with the one we already have. Okay, and I'm going to go with that u prime over u version. It's kind of the more common option. But because my base is something different, I'm going to leave a little bit of space in front because we'll deal with that. But the u prime over u still shows up. The adjustment that we make, natural logs work really nicely in calculus and other bases don't work quite as nicely. And so the adjustment we make is this constant in front, 1 over natural log of a. So 1 over natural log of 5 or whatever it is. And again, I know I'm jumping around slides a lot, but bear with me. If we contrast that with our exponential, right? If my base was something weird on an exponential, then we multiplied by natural log of a. If my base is something weird here, then essentially we're dividing by natural log of a. And it's because they're inverse functions. Those are closely related. If you happen to remember the change of base formula, that explains where this comes from. And so really that's it. The homework helps you practice some of those, but it just comes down to 4 big things that we saw today. So on your purple sheet, it's back in your Unit 2 notes. I think it's the first part of the Unit 2 notes. And so I would write the notes here and then compile them in that Unit 2 section a little bit later. Notice that I've stopped bothering with the x's because I want to go ahead and just include the chain rule kind of as we're working through these. When we started the purple sheet, we hadn't learned the chain rule, and so I had to have x's for everything. But now that we know the chain rule, I'm going to go ahead and just include it so you don't have to remember it as its own separate thing. So we just looked at natural logarithmic functions, and those are the nice ones. 1 over u, and then a fixer piece of u prime. Again, the u prime is nothing new, nothing fancy, nothing special. It's literally just the fixer piece because of the chain rule. That's one way to write it. It's also very common just to write it as u prime over u. If I change the base of the logarithm, so maybe it's log base 2 of u, no problem. It stays basically the same, a u prime over u, just like we had on the left. But we make an adjustment with a constant. So if this were log base 2 of u, then we'd have a constant 1 divided by natural log of 2. Basically what this thing does is it kind of switches it from a bad base that calculus doesn't like into a good base of e, which calculus really likes. And then for the exponentials that we started with today, for any exponential function, it shows up as part of its own derivative. The derivative of e to the u has an e to the u in it. The derivative of a to the u has an a to the u in it. We also have a fixer piece. Nothing new. You wouldn't have to also do the chain rule. We're literally doing the chain rule here. And if the base is e, then you're done. If the base is something else, no problem. Multiply by this constant, for example, natural log of 2, if it was 2 to the u, and you're finished. But something I want to emphasize for the bajillionth time is that on the purple sheet, most of the things, I think maybe all of the things we filled out so far have had x's in them, just because we didn't learn the chain rule until, a week ago. From this point forward, all the derivatives we write are going to already have the chain rule done for you. So you're not going to have to separately write out like y equals e to the u. You're not going to need to do this anymore. And then be like, oh, do I need a fixer piece? The fixer piece is already there. These rules, and including the u prime already, those rules help you do the chain rule faster for these types of functions. And so for our logarithmic functions, the stuff on the inside moves to the denominator, and the derivative goes on top. For an exponential function, the original function stays the same, and then the derivative of the exponent is our fixer piece. So those patterns make this go pretty quickly. For homework 1, you get just a few practice problems with logarithmic and then a few practice problems with exponentials. It's just a matter of doing this enough so that you start to know those rules quickly. But with that does it for me. It's not a super long or terribly complicated set of notes. And so with whatever time you have left during class, go ahead and start on homework 1 just to get a feel for the types of things I'm looking for there. So I will see you soon. Thanks, guys. Bye.